Engineering structures, whether they are towering skyscrapers, underground mining tunnels, massive bridges, or industrial machinery, all have one fundamental requirement: strength. Welcome to this lecture on strength of materials, a cornerstone of engineering that determines how materials behave under different types of forces. Whether you're a civil, mechanical, or mining engineer, understanding this subject is crucial for designing safe and efficient structures. The study of strength of materials dates back to the 17th century, when Galileo first experimented with the effects of loads on beams and rods. Fast forward to the 18th and 19th centuries, and we see pioneers like Saint-Venant, Poisson, Lamé, and Navier refining experimental and theoretical approaches to understanding material behavior. Today, with advanced computational techniques, we continue to push the boundaries of material strength, ensuring our designs meet modern engineering challenges. Before we dive into material behavior, let's review a key principle: equilibrium. Any structure or mechanical component must be in equilibrium, meaning all forces and moments acting on it must balance out. External loads can be classified into surface forces and body forces. Surface forces occur due to direct contact, such as the force of a crane's hook lifting a load, or the ground supporting a mining shaft. Body forces, on the other hand, arise without direct contact, like gravitational forces acting on a bridge or electromagnetic forces influencing metallic structures. In engineering analysis, distributed forces are often idealized as concentrated forces or linear loads to simplify calculations. To analyze a structure, it is essential to identify its support reactions. Roller supports allow movement along one direction and exert only a normal force. Pin supports restrict translation but allow rotation, exerting two force components. Fixed supports restrict both translation and rotation, exerting forces and moments. A free body diagram, FBD, is a crucial tool for visualizing all forces acting on a structure, ensuring that equilibrium equations are correctly applied. This approach is fundamental in structural analysis for bridges, mining tunnels, and machine parts. Once external reactions are known, internal forces within a structure must be analyzed. These forces include normal force, which acts perpendicular to a cross-section and influences axial tension or compression. Shear force acts parallel to a cross-section and causes sliding failure. Bending moment leads to bending deformation and is crucial in beam and bridge design. Torsional moment develops when a force twists a structural element, which is particularly important in mining drills and mechanical shafts. By sectioning a structure and applying equilibrium equations, these internal forces can be determined, helping engineers ensure structural integrity. Stress represents the intensity of internal forces within a material, measured as force per unit area. Normal stress is the force per unit area perpendicular to a surface and affects axial members such as columns and mining supports. Shear stress, on the other hand, is the force per unit area parallel to a surface and plays a crucial role in bolted joints and machine elements. Stress is expressed using Pascal PA in the SI system or PSI, pounds per square inch, in the US customary system. Axial forces act along the length of a member. When a member is stretched, it experiences tensile stress, whereas compression occurs when it is pushed together. The equation for average normal stress is represented as sigma equals P divided by A, where P is the axial force and A is the cross-sectional area. This principle is applied in structures such as suspension bridges, tunnel supports, and steel frameworks. Shear stress plays a vital role in many engineering applications. It is calculated as tau equals V divided by A, where V is the internal shear force, and A is the area resisting shear. Shear stress is present in bolted and riveted connections in steel structures, shaft torsion in mining conveyor belts and drilling rigs, and shear forces in rock formations affecting tunnel stability. Understanding strength of materials is crucial for all engineers. Whether designing tunnels, bridges, machinery, or underground supports, ensuring that materials withstand applied forces prevents catastrophic failures. Mastering these principles contributes to safer, more efficient, and longer-lasting structures.